Hi, I'm Christian.
And I'm Vera.
And in this episode, we're going to show you how we line board Fabians TDV6 diesel engine block.
I hope it's not going to be another dumb idea.
For me, it actually does look like a dumb idea. And I cannot imagine that it's gonna work.
Okay, so I'm going to walk you through the setup I've built to line bore this engine. And going through this step by step. Hope you enjoy the video. Okay, I want to show you how we did this.
Yeah.
Okay, and for doing that, I got to take one main back out.
Is that called a main?
Yeah, this is a main bearing block.
Oh, you should. Yeah, it's a main
There
bearing
it is.
block.
And
Then I know what you're talking about.
I want to get this all dirty. Okay. So, on Fabian's engine block, only the two inner mains got destroyed, as I showed you before. Now there is one unique scenario now here, which I think makes it possible for me to do the boring of this engine myself, and that is that the front and rear mains are still in perfect condition. Destroyed means the bearing races started to spin around, okay?
Yeah.
Okay, they seized up and they destroyed the crankshaft, and in case of a Land Rover, because you know Land Rover owners got more money, it also destroys the engine block. Very simple setup. I should start over.
Stop the recording.
Okay.
First start.
It spun the mains on the two inner bearing races. The two outer ones did not spin inside the engine block, so the bores are still good, and the two inner ones spun around. So the engine needs what's called line boring to get these diameters back to a good condition, because when they spun around they all gumbled up. With that, you shouldn't be able to take this out, and there's your problem. See, this is the bearing shaft,
Yeah.
and they started to turn.
And they're not supposed to.
No, they're not supposed to.
Die ist ganz locker.
Yeah.
And what that means is the block is wasted.
The engine block,
Engine block is wasted.
that thing,
Yes.
so 1,500 euros.
The line boring operation is usually done by a machine shop. So I thought we'd just quickly do this ourselves using my little home shop. I got a hobby lace right here, and I got a small size milling machine right here. So you can see the hobby tools I'm using are not high-end tools, but still they are sufficient, in my opinion, to do this boring operation with a little bit of finesse. Where you can come around here, and I got this loose so I can take this out. You can see this bearing surface when you go here on the side. This is the original bearing surface. I did not touch this, so the bearing did not spin. All I did is I cleaned this up. So this surface is still good, and this one is still good. This one was all gummed up. This one was gummed up, and this one was still good. I'm using now the intact mains to guide my boring bar here. Now, I gotta say, you need an accurate bar. So here I got a high precision 40 millimeter steel rod. It's hollow, it's surface hardened and ground, and it runs out over 1000 millimeters, measured in the middle, TIR 0.01. So this is high precision. The manufacturer is Bosch. You can easily get such a rod from a hydraulic cylinder, cut to lengths from someone for around, I want to say, 90 to 120 euros. In order to make this bar an actual boring bar, I needed to install a cutting tool.
I have only 10% battery left.
As usual. So I take this out. Okay. Look from the top here inside. Okay, here you can see that I drilled a 12 millimeter hole through the hardened boring bar. Now that's not an easy operation, but it's in there. Here is the cutter, which I just took off. I will show you in detail how this is working by mounting it here onto this dummy shaft. This way you can see the mechanism on the inside. look from over here. Now here you can see the cutter is backed up by this pusher. And in between the cutter and the pusher is an adjustable piece of thread. It's like a set screw. And what I can do now is I can use this mechanism down here to drive the cutter upwards and engage it deeper into the material. And this is done by a set screw setup, which is basically taking this wedge and moving the pusher up and also pushing onto the cutter. And I'll show you how accurately this works by putting this dial indicator on here. There. Now look at the dial indicator. I'm going to set the dial indicator to 0. Now what I can do now is I have this piece down here, which is a little 5mm thick brass rod, and it acts like a wedge, wedging up the pusher against the cutter. And the cutter has a set screw here in the side. So I can lock the cutter in place. There is a set screw down here on the other side of this wedge piece. And when I turn this now, look at the dial indicator straight. Okay. I can drive the cutter upwards. I'll do 1 revolution. We set it here to 10. And now I do 1 revolution. So this is half. And this is 1. So it does 0.04 of a millimeter in 1 revolution.
Yeah.
Which means if I do a 1/4 revolution, I have about 100th of a millimeter. It's such a flat taper down here. It is also really solid. So if there is a force acting up on this cutter in this direction, it has a solid backup and not just a set screw. And this makes this a very rigid and fine adjustable cutter.
I don't think anybody can reproduce that.
Of course they can. Any hobby machinist can reproduce such a cutter setup. Okay, first of all, the cutter with the little set screw here on the side is ground out of a 12mm HSS end mill. So the idea is to make now a cutter out of this piece of high-speed steel. It even got already a flat right here, so I can use this flat. Then there is a 12mm hole bored here, and of course a 6mm set screw to go against the flat. And then this whole pattern is just to mount the 2 pieces together. Now, the little more difficult piece is the wedge. So if I take the wedge out, okay, and you can see this is a 5mm diameter brass piece, which has a 1 degree taper machined onto it. I think this was actually about 1.5 degree. I kind of eyeballed this. 1 degree would do it, and my drawing shows 1 degree. I just screwed it up. But it doesn't matter. When I now want to machine the pusher, there is a little trick you need to do. Pusher is quite tight. It's good. Everything is a good fit. It's kind of important that nothing is loose. So this is the pusher. And what you need to do is machine that slot in the same width as the pin. And of course, so that it has 90 degree when the 2 pieces are mating. Okay, and that is really easy. When you machine this piece first, you put this underneath this piece in your vise and use it as an end stop, and then you set it up in your vise and you clamp it. So if this is lying flat in your vise, you set this on top and you clamp it, and that automatically gets you the correct angle, and then you run an end mill here in and out, giving you the 5mm slot, and you're all done. So then this piece is by a hundredths of a millimeter in the correct angle mating to this piece. And you can see this also serves automatically as an anti-rotate by going into here. And then this piece has a 5mm hole drilled through here. And the hole, the 5mm, has the benefit that you can cut your thread 6mm directly into it as far as you want. You want to leave a little bit of guide clearance here, and then you're ready to go. You can go to town with this. So this is a relatively simple setup how you can build an accurate pusher. And the pusher, of course, has to fulfill the requirement that you can adjust it while it is installed in the engine block. This goes in there actually like this. My cutter sticks out, and then I can still get my Allen wrench in here by turning the lower set screw up like this. I can increase it, for example, 1/8 of a turn, and then I lock my cutter down into place using this set screw, and then I can do the next machining operation. And the hard part was to drill this hole, because this boring bar is hardened and ground, so I had to break through the hardened surface here. So I used a angle grinder, and I ground off this area first in order for the drill bit to bite in, and started to make chips. And then I used a 12mm solid carbide drill to get this hole through. So that was not easy to drill through. Part 3 are the guide bushings. Now the guide bushings are also out of aluminum, and they need lubrication during the machining process. And the way these are machined, also very important, is to machine on my hobby lathe the OD and the ID in one chucking operation. You don't want to unchuck this. This way you can get them concentric, even on a poor machine like that, better than 1/100ths of a millimeter. Easy, not a problem at all. And of course you need to use sharp tools, and you use your experience to operate this thing. Now the ID, I got it as close as possible until it got stuck, and then I polished the ID using 320 grit sandpaper until I had a really smooth fit, and I got it to fit. So you have to take a deep breath to get this thing actually on here without getting it stuck. Okay, so it is quite accurate. You need this bushing twice, and the OD of this bushing, you basically machine to the diameter you gauged in your engine block plus 2/100ths of a millimeter in diameter, 0.02. When you torque down these bolts to full torque with this thing inserted, you can actually squish it a little bit. You can squish it, those 2/100ths, which means when I torque these bolts, I can get my boring bar to almost lock up. I made the dimensions not as accurate as I wish, but when I tighten these, I can feel it tightening up, but I can't lock it up. And then you tighten up the screws on this side and tighten up the screws on this side, and you got an extremely concentric running boring bar in the original position. The next step is then, how do you do the actual machining operation? But before we go into that, I want to explain the rest of the setup. I have the luxury that I can turn my mill head horizontally. It's really no good in this position, but it happens that I can turn it. That's the first time I think I ever turned it.
Yeah, it looks weird to me.
Okay, and I got a little bit of an advance here with a crank, and this advances the drill head. Then I use a regular drill chuck, and I have this little crankshaft, been lying around for 20 years. It's from work. It landed in our trash container, and I took it, maybe 25 years ago. You need something to take out the incompliance, and this little crankshaft was perfect. So just one more adapter machined, and done. Now I was able to bore out the two mains to the original diameter of 75 millimeter. Here, I show you this. Yeah, see how nicely it sits in? So you may wonder, how can I bore this out to an original diameter of 75 millimeter when it was all destroyed? And the way this works is when these bearing blocks seize up in the engine, they actually heat up drastically because there is oil starvation. And during this heat up process, they bend. They bend significantly, and they stay actually in this bent position. And because they bend, they narrow up here and they narrow up here, up to a point where this dimension after seizing is less than the 75 millimeter, what that bore actually originally was. And because of this circumstance, you can remachine them and still take off material here on the ends. Very amazing. I did not know that. The top one doesn't get a lot of load when the pistons come down and grind the broken bearing shell through the surface, okay? The load is actually always going down in the lower one when the piston shoots down. So the upper section only had basically scratches. It has some thrown up material and some scratches, but you could already see it when it was still original that the surface could be salvaged. And that's a very lucky circumstance because it allows to bore out this bearing block to the original 75 millimeter. That was the tip I got from my machinist. And here I can show you where you can still see today that this was originally bent, because normally you would not be able to stick this in here by hand. It would actually tighten up, but with a little bit of finesse, I can set this in by hand, and here it has now play. And I measured this play, it's a hundredths of a millimeter.
How?
Maybe 200ths. You measure this by using shim material here. Yeah.
Oh, that's what
So
that
I
is.
gouged this shim material.
It's lying on our kitchen table.
Yeah, I gouged that shim material here in between and I knocked it in with a brass hammer to see how much play it had. But because they are now too short, these are not too short, the outer ones, but this one is too short, I have to make sure that I'm altering the tightening order of the bolts in order to bring this into a repeatable position. That's an important step, because if I would now keep the tightening order from Land Rover or from Citroën, it would not work. I would have that thing somewhere, but not in the center. So, and I marked my tightening order with some drill tips here in the block to make sure I tighten these bolts first. It was all burned up, it was all gouged up here, and it was bent, and it was all black here on top too. The first step in order to get this thing remachined is you have to flatten the back side, okay? Because you want to remachine this side far enough that you can actually take off material here in this area. So the very first step was to measure the bore. And I measured a bore which was 0.6 millimeter larger than 75 millimeters. So I knew I had to take 0.65 millimeters off this end. Now, good machinists do this in a grinding machine, but I did it actually in my mill. So you can still see the milling trace marks here. The first step in order to machine this side off was to clean this side. That's why there is a cleaning cut on here, to get it nice and even, because it was bowed. Makes sense to everyone. So once I had this side machined even and flat, I turned it around, engaged it step by step to take out 0.65 millimeters, because I measured a bore which was 0.6 millimeters over the 75. So this was a very simple machining step. And then I took some 320 grit sandpaper on a flat surface, and I ground the sharp edges from my cutter off so that it sits nice and solid. I did the same thing on the other one as well, except here I only had to take off 0.5 millimeters. Okay, so I did only as much as necessary. Why? Because the old machinist told me. The side bore here had enough clearance for this thing to sink down another 0.65. I think if I would have went 0.7, the bolt would have started to hit, because the bolt has only like 0.5 millimeter of a slot around it, so the hole is 1 millimeter larger, maybe 1.2. Now, once this thing was finished, I installed it in a new tightening order, as explained. When I machined the back side, I machined off the number here, okay? So this is number 3, because the number is etched in right here.
Oh.
Yeah?
Yeah.
So I machined this number off. So make sure when you do your machining that you actually knock the number right back in. And there's the 2. So far, everybody can follow me. Really, really easy procedure.
Yeah.
And then I could install the boring bar for the first time. Works good. Okay, they are now nicely machined and clean. And because they have a little bit of play in this direction, we're gonna have to maintain a tightening order. So we're gonna give it 12 Newton meters to pull the block over in this direction. And we do the same on this block. So the bushings are still somewhat loose. The bar is in, and if we tighten it up now, these bushings should tighten up. 60 Newton meters. Now we got to tighten the side bolts. 33 Newton meters. So 144, we start with bolt 1. Whew. It's still moving.
Absolute wood.
Over here, it was a little bit of a looser fit. I could actually get the 140 and I could feel it just to snug up. This was kind of lucky. If you leave this a little bit larger in diameter and it tightens up too much, you can take it back into the lathe and run a sandpaper over it and get it down. And then I could start with the boring operation. And I did this in stages, okay? I should have done maybe one bore through both of the mains, but I didn't. I was too scared. I finished one until I had it finished, and then with the same amount of work I finished the other one. The boring bar, just take my drive shaft off. I moved it with my drill press basically in and out.
Yeah.
I used the speed of 190 RPM. I did this really, really carefully because once you take off too much, the block needs to be bored out one step further, and that would be terrible.
And then you have to do all 4 of them.
One step you need to do ahead of time is use a Sharpie or some Persian blue, and you basically dye the entire surface completely nice and black. I don't have Persian blue, there is no such thing in Germany, so I had to use something like a Sharpie. This is a really important step. So once I had this then all set up, with the boring bar inside and my cutting tool set up, the boring operation could start. Let's set up the drive shaft. That's good. So I'm gonna give it some alignment here. Okay, I got a small RPM. You set up your cutter and you go by hand this way, in and out, and you see if your cutter scrapes a line into your Persian blue or into your black ink marking. And if it scrapes a line, you're already too deep, and then you back up a little bit until it doesn't scrape, and that's when you can take your first cut. So you're not scraping on the bottom, but you're scraping on the top end. I got it at the end where it scraped all the way around my Sharpie lines, but it did not take them completely off. Then I took my rod out, I polished it a little bit with emery cloth, and I took my measurement, and voila, it was right there. Minus 2/100 of a millimeter from the 75, and that made me smile. And it was difficult. It took like an hour to get that last cut set up where both my dad and I said, yeah, that's good, we're gonna run it through. Because if you screw it up, you're done. Yeah.
Then Fabian needs a new engine block.
So the cutter is installed. Yeah, it's touching, but not on the bottom. So it doesn't scrape on the bottom. And there is a good cut here. So we're gonna do this cut now. Okay, we split our work. My dad's gonna do the advance, and I'm gonna monitor the progress. There we go. Slow. Stop it. And now retract. Yeah. Okay, stop. Okay, next pass. Stop. Stop. Really light pass now. This might be the last pass. And we got here 65 years of experience. Slow. And then we have to remove the bar and take a measurement. It took us whole day to build this rig. We got -200. See it here go to negative? And if I scoop it over to the center, we also got minus maybe 1.5, and then I scoop over to the other side, and that's where it's a little shy. It's a little too big by 100ths, but it's still in the negative. The surface finish, it's not the smoothest, but it looks very even. And started. As fast. Okay. So in order to gauge this, I used my cheap Chinese boring gauge.
Which was actually not cheap.
Well, it was quite cheap. And I used the micrometer. So I need to set the micrometer now to 75. A micrometer actually comes with a 75 millimeter gauge block. That is now, of course, a lucky circumstance.
And that we have it.
For 20 years. So
25.
So I set this up to 75, okay? There. I clamp this. And I gotta be able to kiss the 0.
Are you?
Yeah. See, it's 200 shy. Now I give it 200s more. Yeah, I think it's quite accurate, right? I'm kissing the 0, okay? Now I got 75 millimeter, in my gauge. Here we got the measurement of the original Ford machine bore, yeah, which did luckily not get destroyed. And you can see here, now go to the gauge, you can see this is a little bit in the minus, yeah. Depending on where I go inside the bore, I can even see that it's not completely plain, but it's, I would say, minus 200. On the other side of the oil bore, you have to go over here on the needle. It's the same, minus 200. And here's the bore I machined. Now, so here, set this in. I would say I have it even a little tighter, like 300ths. On this one, I got the dimension more accurately. The reason is that the block side was not as gouged up. Okay, so the cutter was easier to adjust and easier to see in my Sharpie lines. So that one is probably 100ths to 1.5 too tight. I used then 800 grit sandpaper, go over this very lightly. I think this looks really, really decent for a home machine job. Once these bearings are here installed and the bolts are torqued, the engine block goes over to my machine shop, and he's gonna do the crankshaft grinding, each main mating exactly up to the engine block. This way we can salvage the old crankshaft and we don't need to spend 1,000 pounds on a questionable crank. This is the original crank, and he's gonna match the mains exactly to the engine block. So that's gonna be an excellent fit. So that's it. That's the next step. How we're gonna get now the crankshaft fit to our line bored engine block.
Didn't sound all that stupid.
Okay, the line boring is complete and as accurate as I can get it with my basic machine shop tools here. If you liked what you saw, think about subscribing to our channel, and in any case, as always, please do not unsubscribe. And we'll see you
Next Sunday.
And they didn't even break a single stone. I wonder how they got it out.
So here we got our high-speed internet connection. You can see here they took out these blocks and they ran below the grass with a rocket, and they came up here. So they took my blocks out here, and then the cable went over here, and there they had to go underneath the road from over there. So they dug a trench over there connecting to the high-speed internet cable, and then they shot their rocket below the pavement, getting to over here. Yeah. So I know how that works because I laid every single block in my driveway myself. Not Vera, me. Every single one.